Okay, good afternoon, everyone. Right. So today, we continue on chapter 7. Right, the last chapter. Okay. Quantum theory of light. Right. So this one actually I use the notes from the textbook. Okay. If you yeah you can use the notes also that I give. Okay. But that one they explain to you like very too detailed. Okay. So I use the textbook. Okay. So for this one is a quantum theory of light. Okay. So this when the modern the modern physics start. Before this we use a classic physics, right? So now it started with the quantum theory, right? We start the modern physics. Okay. So in form 4, okay, the real form 4 you learn chapter wave, right? So wave chapter it says that electromagnetic spectrum is a continuous spectrum. So electromagnetic Okay, so electromagnetic spectrum is a continuous spectrum. So actually, electromagnet is the example of the transverse wave, right? Okay, so it's a continuous spectrum. Okay, the one that have a gamma, X-ray, ultraviolet radiation, and then you got visible light. Okay, so this visible light is actually the color of the rainbow, right? Roy G. Biv. Okay, Roy G. Biv. Okay, if you still remember, right? If you learn for the interference of light, right? So the color, okay, the wavelength of the color affecting the distance, okay, of the x, right? Okay, so this is the lambda will be decreased. Okay, so infrared radiation, microwave, and also radio wave, right? So it's a continuous spectrum. So this spectrum consists of 7 types of wave with different frequency, okay, and wavelength. So every type of the electromagnetic wave, all right, they have their own frequency, have their own wavelength. Okay, and this spectrum consists of 7 types and different frequency and wavelength as shown in figure 7.1. 7.1. So from gamma to the radio wave, okay, the left wavelength will be increased. Okay, but for from radio wave to the gamma rays, okay, the frequency will be increased. So it's opposite, right? So the next part then we take for the visible light. Visible light is the one that we can see, the color, right? Let's say the color of the car, whether it's red, black, or no black means like red, white, okay. So that one is the one example of the visible light, okay. That one we can see with our own eyes, okay. So all objects emit electromagnetic radiation. Okay, so cold objects, okay, cold objects emit waves with low frequency. So low frequency, okay, for the cold objects, okay, such as a radio wave or microwave. While the hot objects, okay, they will emit the wave with higher frequency. So means when the hot object, the frequency is higher. Okay, for the cold objects, okay, it will emit the low frequency. Okay, such as visible light and also UV radiation. Okay, so this one, the human always also emit electromagnetic radiation. So yes, okay. So a black body is an idealized body that is able to absorb all electromagnetic radiation that fall on it. So a black body can also emit thermal radiation depend on its temperature. So the black body is actually the one that absorb all the electromagnetic radiation. Okay, whether it's a gamma, X-ray, or visible light, okay, they will absorb all of it. Okay, so it also can emit the thermal radiation. It depends on the temperature. So the radiation emitted form a continuous spectrum and is unaffected by the nature of the black body surface. Okay, it means like whether the size of the object, right, the size of the object, or the type of the material of the object, okay, is not affected. Okay, so the radiation emitted form a continuous spectrum and is unaffected by the nature of the black body surface. Thus, an object emitting electromagnetic radiation, which is determined by its temperature, is known as a black body radiator. Okay, so if an object it can emit the electromagnetic radiation. Okay, so by its temperature, according to its temperature, okay, it can emit the electromagnetic radiation based on the temperature. We call it as the black body radiator. Okay, so this one also they explain to you what is actually a thermal radiation. So thermal radiation is the electromagnetic radiation that includes visible light and radiation that cannot be seen by the human eye, such as infrared radiation. So our eyes cannot detect the infrared radiation. Okay, so the one that we can see is only for the visible light. Okay, so the thermal radiation is electromagnetic radiation that includes the visible light, the one that we can see, the color, okay, and the radiation that cannot be seen by the humans, such as infrared. You cannot see the infrared, you cannot see the radio wave, we cannot see the microwave, right? Okay, so that is called as thermal radiation. Okay, so the black body actually it absorbs all the electromagnetic radiation. Okay, it absorbs all the electromagnetic radiation. Okay, so that's why we call it as the black body. Okay, and it also emit radiation depending on the on its temperature. Okay, so let's say this is the example. Okay, so in your ears, so if you see in your ears, right, it's a dark. Okay, you cannot see anything. Okay, it's a dark. Okay, so the ray of light that enters the ear cavity, okay, will undergo repeated reflection. So when they say this is your ear cavity, then the light come okay inside the ear cavity, then they will be reflected. Okay, they will be reflected many times. Okay, so at each reflection, part of the rays are absorbed. So when the reflection occur, right, it will absorb okay a part of the light. Okay, a part of the light. Okay, so when because there's so many times if the reflection occur inside the ear cavity, so mostly all of the light is being absorbed by the inner wall. Okay, so thus the ear cavity acts like a black body. So that's why we cannot see inside our ear, because when the light enter the ear cavity, they will undergo okay repeated times of the reflection. So whenever they're being reflected, the light also will be absorbed, okay, by the inner wall. So okay, then after that it will decrease at the light ray, the light intensity will be decreased. So decrease. Then after a lot of time, okay, so there will be no more. Then there will be a dark, become dark. Okay, so that is an example of the black body black body. Okay, this is an example. So as the temperature of an object rise, the object act as a black body radiator, okay, and emits thermal radiation of all wavelength. So if you keep increase the temperature of the object, right, the object that act as a black body radiator and emits radiation of all wavelength. So if you keep increase the temperature, this is what will happen. It will emit the thermal radiation of all wavelength. Okay, so this is the figure, okay, the graph for the radiation intensity. So radiation intensity against wavelength of three types of black body at different temperature. So when you increase the temperature of the black body radiator, okay, it will emit the thermal radiation of all wavelength. Then we can see the graph here, okay, the radiation intensity against wavelength, all right, of three types. So the first one is the blue star, white star, and also the red star. So this is the example. Okay, so it says here usually every curved graph of the black body spectrum is narrower on its left. So let's say if I divide, okay, this is the middle, so you can see this one will be narrow, right, and this one will be wider, right? Okay, so it usually every curve of graph of the black body spectrum is narrower on its left, okay, which is an area with shorter wavelength. So now the graph is lambda against radiation intensity, right? So here the wavelength is smaller than this part. Okay, so it says here with shorter wavelength and high frequency. So at this part, the wavelength is shorter, but the frequency is higher. Okay, the frequency is higher. So with increasing the temperature, the wavelength approach maximum radiation intensity will also get shorter. So when you increase the temperature, okay, the wavelength approaching maximum radiation intensity will get shorter. Okay, so it will get shorter. Okay, it will get shorter. So the higher the light intensity of the black body, the more light energy it emits. So means the light intensity or the radiation intensity. So means the brightness, okay, the brightness of the color. So the higher the light intensity of the black body, there will be no more light energy that will be emitted. Means the light will be brighter. Okay. So this is the graph of radiation intensity against wavelength. Alright. So this is the example, okay, thermographic image of car, okay, or during the COVID time, right? Usually they put this one at the mall. So whenever you pass by, you can see say if your body is in the hot condition, right? Then it will become like, okay, this one you will be like look like red, right? So that is also the example, okay. And this is the oven heating element. Okay, you can see inside of the your oven. Okay, there's like a coil there. Okay, that one is used to heat the oven. Okay, and this is the bulb. Okay, so you can see the thermal radiation in light bulb at different temperature. Okay, so the temperature is higher. You can see the light become brighter, right? So this is the graph of radiation intensity against wavelength. All right, this is the visible part. Means at this part you can see the color, right? The rainbow color, RGB. Okay, beef, red, orange, yellow, green, blue, indigo, violet. Okay, so at this part. Okay, so this is actually the basic theory. Okay. But then ideas that spark the quantum physics theory. Okay. So what happened? Okay. What does happen? How come that we can say that suddenly, all right, the light is actually like a particle. Okay, it's a wave particle duality. It can be like a pack of object. Okay, pack or maybe they can be like a wave. They can act two 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 how do I say this? Two characteristic. Okay, it can be a pack or maybe can act also as a wave. Okay, that one we will learn later. Okay, so ideas that spark the quantum physics theories is light is an electromagnetic wave that is produced by vibration of the electric charge. Okay, so when the electric charge vibrate, okay, it can form the light. So light is the example of the electromagnetic wave. So in a hot object, electrons vibrate rapidly. Okay, so this one you already know. Okay, when you apply a heat, okay, for the object also or to the atom, they will vibrate rapidly because kinetic energy. Yeah, you give to the energy, heat energy, we turn into the kinetic energy. So that's why it will vibrate rapidly. Okay, and randomly in any direction and produce light. Okay, so they will vibrate and randomly move in any direction and produce light. So as the object become hotter, the vibration of the electron become more energetic. So this one, because if you apply more heat energy, means the more heat energy will turn to the kinetic energy. So the kinetic energy, then the electron will move faster. So the vibration now become faster, right? And more light will be emitted. So when the more light, more energetic means more light. Okay, so more light will be emitted. So the electron in a hot object will vibrate in continuous frequency range. So they will keep vibrate in the continuous frequency range. Okay, so how many hertz? All right. So according to a classical theory, okay, electron vibrating at the same frequency should have the same energy. Okay, so according to the classical theory, all right, so it says the electron that vibrate at the same frequency must also have the same energy content, right? Because they have the same frequency, it means they will vibrate at the same time. What does that mean by frequency? Frequency is the number of oscillation, right? Let's say 1 second. So when they vibrate, they mean the same frequency, so the energy also must be same. Okay, but all right, the vibration of frequency of the electrons also have no limits. Okay, they don't have no limit, means they can vibrate how fast they want. Okay, thus the light energy produced by the vibration electron can reach unlimited high values. So it can vibrate, it can produce, the light energy can be produced, okay, in unlimited. Means you cannot, we don't know what is the value. Okay, as long as vibrate, right? As long as it will vibrate, okay, it will keep continue producing the light energy, right? So, however, experiment result involving black body radiation are inconsistent with the classical physics theory. Okay, so but when we do the experiment involving the black body radiation, okay, are inconsistent with the classic physics theory. Okay, the one that we said that if we vibrate if the electrons move, okay, with the same frequency, then the energy also must be same. Okay, vibrate with the same frequency, then the energy is also must be same. But in the black body radiation, it's not like that. Okay, so based on the graph the radiation intensity against wavelength for the black body radiation, the light intensity on the left side of the peak does not continue to increase with the increase of the wave frequency as predicted by the classical theory. Okay, so by using the graph, right? Okay, at this part, it's not doesn't increase. It doesn't increase continuously, right? It doesn't increase as the wavelength increase, the light intensity also increase. No, because you can see here, there will be go down like that, right? It go down like that if that black body radiation, okay, for the black body radiation. So it doesn't follow the classical theory, okay, that is said when you increase the frequency, then the light intensity also will be increased, right? But this one, if you increase also, it will decrease. So it doesn't obey the classical physics theory. Okay. So this controversy in the concept of light energy has sparked the theory of the quantum physics. So this is the start of the modern physics. Okay. So the classical one is starting from the Newton. All right. So first Newton said, okay, the part of the nature of light, the particle is the nature of light. So describe light as the single stream of particle or corpuscle in 1704. So unsuccessful in explaining the phenomenon of light or refraction due to failure in comparing the speed of light in glass and air. Okay, if this one come out also in the exam, I think it's only come out for the paper one. Okay, so it's just a knowledge. Okay, so maybe if it come out as a paper one. Okay, in objective questions. All right, so that's what Newton said. Okay, it's a single stream particles. Okay, or corpuscles in 1704. Okay, this is when it found this theory. So unsuccessful in explaining the phenomenon of the light refraction. So light refraction means the light is reflected away, okay, if from dense to the less dense, right? So then it failed to compare the speed of light of glass and air. Okay, there is n is equals to c over v, right? Okay, then the Thomas Young, okay, this one is actually the double slit experiment is the interference. Okay, interference Young double slit experiment, that one. Okay, they got two gap there. Then let's say we put the water, then the water, this is if you still remember, okay, there is a gap, right? Yeah, two gap. Then let's say if you put two source of water, okay, this is the interference, okay. So this is the experiment, double slit experiment. Okay, so conducted double slit experiment on light, okay, in 1801 and shows that the light is a wave. Okay, so this is the proof that actually light is a wave because we know the characteristic of the wave. Okay, that can be diffracted, reflection, right? Interference, diffraction. Okay, so they can undergo all the phenomenon of wave. Okay, such as reflection, refraction, interference, and diffraction. So light can undergoes all that wave phenomenon. Okay, so this is the proof. Okay, but however, is unable to explain the radiation spectrum produced by the black bodies, right? But it cannot explain the radiation spectrum, okay, emitted by the black bodies. because the black bodies, right, you can see when the wavelength is increased, okay, it increase at the first part, then after that it going down. Okay, but then the Dalton atomic model. Okay, so this one I think you already know. Matter consists basic particle that cannot be further divided called atoms. Okay, so that is the basic. The atom is the smallest. Okay, but same element have the same type of atom and unable also to explain the light spectrum produced by atom. So this is a John Dalton discovery. Okay, then after that the J.J. Thomson, okay, discover the negatively charged subatomic particle called electrons. So me inside the nucleus, right, we know they got a proton and neutron inside of it, while the electron is orbit, okay, around the nucleus. So it design experiment to study behavior of electrons, but however is still unable to explain the line spectrum of light produced by atom. So this is the classical theory, right? So if you want to read more, then you can just scan this QR code. But then we start for the modern physics. So it start with the Max Planck. Okay, so it say introduce the concept of quantum discrete energy. Mean is moved by a pack. So it's like a pack. Okay, so mean light is travel like a pack. Okay, a pack of atom or okay, so it like a pack there. Okay, so that's why later we learn about wave duality. It means they can act as a wave and also for the atom, like also as a pack of object. So the electromagnetic wave emitted by a black body is in discrete form known as a quantum of energy. So the Max Planck introduced the concept of quantum, okay, in 1900. So it says the electromagnetic wave emitted by the black body is in discrete form known as a quantum of energy. Okay, then the energy is each quantum is directly proportional to the wave frequency. Okay, so the energy of each quantum, okay, is directly proportional to the wave frequency. Okay, this one we look later. Okay, so the electromagnetic wave the electromagnetic wave emitted by the black body is in discrete form known as the quantum of energy. So this one they will explain to you what is the mean by quantum here. Okay, the intensity of the radiation is low for the high frequency. So when the high frequency wave, the intensity of radiation is low, means it's not that bright. Right. Then the Albert Einstein, okay, introduced the photon concept in 1905. Okay, the photon energy is directly proportional to the light wave frequency. Okay, then it introduced the photon concept. So the photon energy, this one I think we learn E is equals to HF, right? Directly proportional to the light wave frequency. So instant quantum theory light was successful in explaining the characteristic of photoelectric effect that could not be explained by the classical theory. So just now, right, they try to by their own discovery for each physicists here, right? They find a new thing, but however, it cannot explain the line spectrum of light. Okay, it cannot explain. But then, okay, the Albert Einstein, right? It can successfully in explaining the characteristic of photoelectric effect, so that could not be explained by the classical theory. So they introduced the concept of photons here. So I turn quantum theory light, later we will see that one. And Niels Bohr, right, explaining the production of line spectrum by hydrogen atom. Okay, so the electron in atom orbit around in nucleus of certain shells only. Okay, this one I think you also learn the Bohr model of atom, if I'm not mistaken. So the transition of electron from a higher energy level shell to a lower energy shell, lower level energy level shell emits photon. So this one the electron jump, right? I think you learned that one in chemistry. Okay, and Louis de Broglie, okay, introduced the hypothesis of wave nature of particle. So Einstein and de Broglie postulated that idea of wave particle duality of light. So mean it can act as a two, and so it can also can act as a wave, Okay, at the same time, because light can also be refracted, deflected, reflected, right? So it can follow the wave characteristic, but at that time, at the same time also, they can also act as a atom, a pack. Okay, that one I will explain later. Okay, and all subatomic particles. So this one is actually the history. Okay, the history of the quantum theory. So this one maybe you just need to remember what is the in the what is the discovery that made for each scientist here. Okay, starting from the classical to the modern physics. Okay, now we see for the quantum of energy. So first, it says here that electromagnetic spectrum may be continuous spectrum or a line spectrum. So every color, so let's say if I take the visible light, okay, let's say I take the visible light. So visible light, every color of it, they got their own wavelength, right? They got their own wavelength. So the electromagnetic spectrum may have a continuous spectrum or line spectrum. So figure 7.4 and 7.5 shows example of the continuous spectrum. So this is a continuous spectrum. There's no like the the border, right? We did it change exactly. Okay, this part, okay, that we of confirm change to blue. Okay, you can see the color suddenly become blue, then suddenly it become green, suddenly become yellow, suddenly become red, right? So that's a not that exactly aligned. So this is a visible light spectrum, the continuous spectrum. Okay, there is no a border, right? A border to say, okay, this is when the suddenly the green will become yellow. No, yeah, then this just like a transition is very hard to see. Okay, but if the line spectrum, okay, but this one we use the hot mercury vapor length. So this one is the exactly, right? You can see, oh, this is the line. So this one is the yellow part. Okay, this one is the red, right? And this one is the blue. Okay, this one is the purple, or we call it as the violet indigo. Okay, so this is a line spectrum. This is a continuous spectrum. So the dispersion of white light, okay, so we know that if we combine all the color, they will produce the white light. Okay, so the dispersion of white light by a prism, by a prism produce a continuous spectrum consists of 7 visible color. So if you make the white light, okay, so let's say if I have a prism there, okay, then you put the white light here. Okay, let's say if I have a screen here, or maybe the white paper, then the color will be from to 7 visible color that we already know RGB, the red color of the rainbow, right? So this spectrum has a wavelength range from 400 meter to 750 400 nanometer, not okay, for 400 nanometer to 750 nanometer. So remember, nano is 10 power of negative 9. Okay, and the visible light spectrum is said to be continuous because there is no separation gap between each color. So why we call it as a continuous? Because you can see there is no separation gap, right? There is no separation gap between each color. So let's say if I have, okay, let's say this is a blue, right? So blue, then there is a gap here. Okay, then this one started to be green, right? So no, there is a no separation gap, okay, to distinguish every color. So the light spectrum produced by an excited atom is a series of color line with unique wavelength and frequency. But in the line spectrum, okay, is produced by the excited atom. Because you know we learned already, right? You give the heat energy to the electron, then electron will become will move faster, it will vibrate faster, then it will emit a certain radiation, okay, that can produce the color. Okay, so that's what the line spectrum produced by excited atom is, a series of color line with unique wavelength and frequency. Okay, so each element produces a spectrum with a series on its own distinctive line. So therefore, the line spectrum can be used to identify the presence of an element. So this table 7.1 shows the shows the frequency and quantum of energy values of the line spectrum produced by a mercury vapor lamp. Okay, of course, we know lamp also they will produce the heat energy. Then the heat energy will be absorbed by the electron. The electron will move, vibrate faster. Okay, so when it vibrate faster, it will emit the radiations. Alright, so that radiation, in a certain wavelength, okay, they can produce a certain color. Okay, so this is the example violet. Okay, so the frequency is 7.41 times 10 power of 40. When the energy at quantum is 4.91 times 10 power of negative 19. Okay, so this is the example, okay, for the color. So this one you don't need to remember. So let's see, right? So let's say if I put the color here, right? G, if. Okay, so it start from the yellow, green, blue, violet. So I mean we see on this part only. Okay, based from the table here. So the frequency, okay, the frequency from here to here, okay, from the see I take from the yellow, right? So from the yellow to the violet, the frequency is increasing. Okay, the frequency is increasing. Okay, but then we see also for the energy quantum. Okay, the energy quantum, so you can see the value also is increasing. So from yellow to the violet, okay, the energy also increasing. Okay, so means it depends on the frequency. Frequency means what? The vibration, right? The vibration of the movement of the electron particle. Okay, since we apply the heat energy to the electron. Okay, so now the quantum of energy, what does it mean? The quantum of energy is discrete energy packet. So this one I said just now, packet and not a continuous energy. Okay, it's actually a discrete energy packet. It's like a packet, alright, and inside of it is an energy lah. Okay, and it's not a continuous. Okay, like this one. Okay, so it says here the energy depend on the frequency. So that one I already said just now. Okay, it depend on the frequency. So according to the Max Planck and the Albert Einstein quantum theory, the light energy exists in the form of energy packet known as a photon. So the energy packet that I mentioned just now, we call it as a photon. So every packet, they say I have a 2 packet of energy means 2 photon. That's an example. Okay. And what is a photon? Photon are the light energies, are light energies transferred in quantum of energy. Okay, so what is a photon? Photon is actually the energies, a light energies that transferred in quantum energy. How many energy? It's like a packet of energy. So packet, let's say this is the packet. Okay, so this one means 1 packet, 1 photon. Example. Okay. So photon are light energy. So inside of it, they said a packet of energy, right? So what type of energies? Is a light energy. So inside of it is a light energies that will be transferred in the quantum of energy. So the photon energy is directly proportional to the frequency of light. Okay, so means the photon energy, the light energy. Okay, so the light energy inside the packet of it, this one, inside the packet of it is directly proportional to the frequency. So if the frequency increase, the amount of the light energy inside this packet also will be increased. Okay, so the photon energy. So this packet, we call it as a photon. Okay, this is okay, and then the higher the frequency of light, the higher the energy quantum of photon. So this is the formula. E is directly proportional to F. Okay, so E equals to HF. H is the Planck's constant. Okay, that is 6.63 times 10 power of negative 34. And F is the frequency of light wave. Okay, and E is a photon energy. So light is a type of energy electromagnetic wave also. It also behaves as a particle. See? Then after that, we can form the wave particle duality. That one means it can also act as a wave, and also it can act as a particle. Why it can act as a particle? Because it can undergo the reflection, diffraction, right? Interference. That one is the wave phenomenon, right? Then the light also can undergo that phenomenon. Means it's a proof that that the light is a wave. Okay, but at the same time, light also it can act as a particle. Okay, because it when because we describe, right, the energy is in a packet. Okay, in a packet. So we can call it's a discrete energy packet that we call it as a photon. Okay, this is like a particle, right? It's a packet, a particle. So then it also depend on the frequency. So means the light can act as a wave and also as a particle. Okay. So one type of wave in the electromagnetic spectrum can also behave as a particle. Right. So that's the one that we try to show. Okay. So compare the energy of 400 nanometer and also 750 nanometer. So we use the formula E is equals to HF, sorry. So we know that the E is 400 nano. Please remember um the prefix, okay? Because I'm worried just now, like when you answer for the trial exam, right? There's a lot of you didn't memorize, okay, for the prefix. It's very important. You have to know, at least for me, okay, the one that is important for the prefix is usually that we use centi is 10 power of negative 2, okay, or kg, kilo, 10 power of 3, okay, and micro, 10 power of negative 6, nano, 10 power of negative 9. I just told you what is the frequent prefix that usually they use, okay, in the exam. And then they see sometimes 10 power of negative 1. Other than that, micro, nano, pico, seldom, mega. Mega sometimes also can be used because the frequency of the radio, right, is a megahertz. So mega 10 power of 6. At least you remember that one. Okay, I know it's very hard for you to remember all of it, but the frequent prefix that be used is mega, kilo, okay, milli 10 power of negative 3, centi 10 power of negative 2, micro 10 power of negative 6, nano 10 power negative 9. Usually they will always use that one. Okay. But it's better for you to remember all lah. Okay, itu yang terbaik lah. Alright. So we have E is equals to HF, right? And the Planck constant already given in the question. If they don't put in the question, you have to refer to the formula. Sometimes they put it in the formula. And the speed of light is 3 times 10 power of 8. Okay, and this is the wavelength given. Okay, the wavelength given is 400 times 10 power of negative 9 meter. Oh, this one compare the energy. Oh, so this one means the wavelength. Okay, the energy should be in joule, right? Okay, so this is the wavelength. Okay, so the wavelength 400 times 10 power of negative 9, 750 times 10 power of negative 9. Okay, so the first one, C is equals to lambda F. Okay, C is equals to lambda F, then F is equals to C over lambda. It's actually is come from here. V is equals to F lambda. Okay, V is actually a speed, right? And also you know light is the electromagnetic wave. So the speed of the electromagnetic wave, okay, electromagnetic wave is same as the speed of light. Okay, so your C is actually equals to V. Okay, so 3 times 10 power of 8. So remember, the light is have the same wavelength as even in the, they see any electromagnetic, okay, electro type of electromagnetic wave, okay, inside that gamma, UV ray, okay, the characteristic they move with the speed of light, that is 3 times 10 power of 8. So if you asking me why suddenly C is equals to lambda F, it's actually come from the V is equals to lambda. But this one V is the speed, right? So they just put the value C here because it's same as the speed of light. Okay. So 3 times 10 power of 8. Okay, then F is equals to C over lambda. Okay, they arrange it back. Okay, F is equals to C over lambda. Then they use the formula E is equals to HF, right? So they just replace the F, okay, with this equation. So we will get HC over lambda. Okay, so this one come from here. Okay, V is equals to F lambda. Then F is equals to V over lambda or C over lambda. Okay, then you replace, you got this equation, HC over lambda. Okay, then you just straight away put it in the formula, right? So you will get this answer. Okay, so this is your H, this is your C over lambda. All right. Teacher, if I want just straight away to remember this formula, also can. But the basic also you have to remember this one. Because why we cannot directly use E equals to HF? Because the question doesn't give you the frequency. So we need to find other way to find the value of frequency. We learned that it also can act as a wave because light also is actually a wave, right? So we can use the formula V is equals to F lambda. So your F is equals to V over lambda. Okay, you just arrange the formula back, put the F as a subject. Okay, then you can just put it in there and then you just calculate. So here we can conclude that the shorter of the wavelength, the higher the photon energy. So means when the wavelength is short, it has the higher photon energy. Okay, next part, wave particle duality. Okay, so wave particle duality, this is the one that I said just now. Okay, the light also can act as a wave. Okay, what is the proof? Because it can undergo the phenomenon of wave. There is a reflect. Light can be reflected, can be diffracted, can be interference, right? Okay, so it can act as a wave, light. All right, but at the same time, okay, they can also act as a particle, right? Because we assume, right, the energy of the light move in the packet, okay, in a packet that we call it as the photon. Okay, so electromagnetic radiation such as light is said to have a properties because it exhibit the phenomenon of diffraction and interference. Okay, this is what I told you just now. So objects like a marble are said to have a particle properties because they possess a momentum and kinetic energy can collide with each other. Okay, then objects like a marble, okay, we call it as a particle because they have a momentum. Once the object move, right? Once the object move, of course it will have the momentum because momentum is P is equals to mv. So when it move, of course they have a velocity. So when they have a velocity, they will have a momentum, right? And also it has a mass, right? So anything with the mass have mass and moving. Okay, let's say if you're walking, okay, I mean walking on the road or walking on the road, so you have a momentum. Okay, so any object that have moving must have the momentum and also must have a kinetic energy. Okay, so because E is equals to half mv square. So since it has a velocity, of course it will have the kinetic energy. And also it can collide with each other to produce the, let's say usually for the atom collide with each other, of course can produce the elastic collision, right? Because when they collide with each other, they will be separated, move in the separated ways, okay? Or maybe move in the same way but are not attached to each other, okay? So that also is a particle, is the properties of the particle. All right, so in 1924, okay, Louis de Broglie, okay, oh, they said de Broglie, all right, right. Usually I heard people say Louis, okay, de Broglie, oh, okay, 1892 to 1987, okay, a quantum physicist has put forward a hypothesis. Hypothesis, what does it mean? It's only a suggestion. It's not still proof correct or correct. It doesn't prove the assumption is correct. Okay, that's why we have to do the experiment. Okay, to prove that it's correct. It's just a hypothesis. Okay, it's a suggestion, right? Stating that all particles can exhibit wave characteristic. However, it is experimentally difficult to show the wave characteristic of a particle with large mass. Okay, so we cannot put, let's say we use a car, okay, to say that actually a particle also can follow the wave particle. So we cannot do that by using a large mass. So Louis de Broglie, okay, predicted that the wave characteristic can be exhibited by light particles, because light particle, of course, that the mass is very low. Okay, we cannot use other object because it's very heavy, so it's hard for us to prove that it also can follow the wave characteristics. So for example, electrons. Okay, so he stated that relationship between the momentum of the particle and the wavelength lambda as follows. Okay, so lambda is equals to h over p. Okay, lambda is equals to h over p. So lambda, this is the wavelength of the light or of the particles. H is the Planck constant. P is actually the momentum. Okay, and this is the value lah of h, right? So we just replace p is equals to mv because momentum is mass time velocity. Okay, so we just replace p h divide by mv. So since the value of h is very small, because 6.63 times 10 power of negative 34, right? So the particle of the large masses we have, the de Broglie wavelength are too short to be detected. Okay, since the h value is very small, okay, 6.63 times 10 power of negative 34, right? So the small particle of large mass. So if the mass is large, okay, so the wavelength is very short. Say if you just divide, okay, let's say if I use a car or whatever, the mass is very high, right? So when the mass is very high, you divide it with the smallest number, okay, you almost get it like very small wavelength, right? Because you divide with the very big number. Okay, this one is only 6.63 times 10 power of negative 34, means like 0.0000, right? So 0.00000. So it's very small. But then you divide it with a large number, then your lambda will become too small. Okay, so it's hard for it to detect. Okay, to detect. So therefore, the wave characteristic cannot be observed. Right? So that's why we use a light. So that's why we use a light. Okay, so in 1927, the presence of the wave properties of electrons was confirmed through electron diffraction experiment. So this is the diffraction pattern of electrons, because electrons are very small particle, right? So it's a very diffraction pattern of electrons through a thin layer of graphite. Okay, and then the photograph 7.2 shows the different diffraction pattern. What does it mean by diffraction? So remember, diffraction come out in the exam, if I'm not mistaken. Some of you put it refraction. Okay, so for diffraction, if you see one gap, okay, there is a one gap. Okay, the light or the water wave or sound wave or any type of wave that pass through one gap, this is called as a diffraction. If reflection, there is no gap, right? You just have one barrier, then one plane, right? Not one barrier, one plane, okay, and then will be reflected. This is a reflection. This is a diffraction, okay? Then the light enter they say the water wave enter the gap, then can produce the semicircular wave, right? But it depends on the opening. Or if they don't put a gap here, they put an obstacle. Okay, so the length have to pass through the obstacle. All right. So this is also a diffraction. So make sure you know how to differentiate between wave phenomenon. What is refraction? Refraction must come from the two medium that have different density. Let's say let's say air to glass. Okay. So that different, the light travel to two different medium, right? Yeah, with different density. That is the refraction. Reflection, only one plane, then it come back. That is a reflection. Diffraction, one gap, or also a barrier, there is a diffraction. Interference, two gap, must be two gap. Okay, or they mention it Young double slit experiment. Young double slit is interference. Okay, so that one I will try to discuss later. So especially for the light lah. Okay, I see that your weakness is on the light part. All right. So this is now we come back. So diffraction pattern. Okay. So means the light can be diffracted. Okay. So remember why we cannot use the particle that have a larger mass, because if you have a larger mass, the h is already small. Then you divide it with a bigger number. Then your lambda is too small, so you cannot detect, right? It's hard for you to read the result. Okay. So the de Broglie wavelength of an electron beam is approximate 1,000 to 10,000 times shorter compared to the wavelength of light. Okay. So the de Broglie wavelength of an electron beam, so it's very small. Okay, it's very short if you compare to the wavelength of light. So this property is very important for higher magnification of electron microscope. So the electron microscope is actually by using this property. Okay, so you need to have 1,000 to 10,000 times shorter. Okay, compared to the wavelength of light. Right, so a comparison between the image produced by the optical microscope and electron microscope. So this one is the one that you usually use in the lab, in the bio light, right? So you can see, okay, the magnification is small. You cannot see very clear, right? But this one, it can make uh, the the specimen become larger. So this is the image of red blood if you see under the microscope, okay, in the lab microscope. So you can see it's only just like a very tiny round. Okay, this one, see, can see the cell, the red blood cell itself. Okay, so this is the a comparison. Okay, if you use an optical microscope and electron microscope. So this property is very important because the de Broglie wavelength of electron beam is approximately 1,000 to 10,000 times shorter. Okay, it has to be shorter so you can see it more clearly. So electrons are said to have wave particle duality because they exhibit the properties of both particles and wavelength. Light also possess both wave and particle properties. Therefore, light and electrons are said to have a wave particle duality. It can act as a particle and also can act as a wave. So this duality is found in all kinds of radiation in EM spectrum, that the one we learn gamma, radio wave, visible light. Okay, all that also they obey this wave particle duality. Okay, so as well as a subatomic particle size of proton, neutron. So proton, neutron, electron also they will undergo this wave particle. Means they also can act as a wave and also can act as a particle. That particle that we can put it in the packet, right? In the packet form. Okay, and they have also they have the momentum. Okay, they have a momentum, right? So that's why what we prove that actually all the subatomic particle and also the EM wave is actually is the wave duality, wave particle duality. Okay, so this is the formula, all right? Since they have a mass, so of course they have a momentum. Since it move, of course it will have a kinetic energy. All right, so this is the formula that we learned just now. Okay, problem solving. This is the okay. Wait, I see first. All right. So okay, this one we can continue tomorrow. Okay, so I just finished until here, right? No, not me until here. I mean, let me finish until this part. Okay, then we continue 7.2 tomorrow. So I try to finish during 3 days holiday. Okay, and 5M you have extra class with me. Then the one that your kan time you cuti tu kan. So I will have that one, we finish chapter 6. Then after that I'm planning to do for a revision. Okay, so problem solving for photon energy and power. So energy for one photon mean one packet. Okay, remember I said just now the light energy is travel in the packet. So one photon, one packet. Photon is actually the energy, the light energy. Inside the packet, they have a light energy. So if you increase the frequency, then the light energy also inside the packet will be increased. Okay. So assuming the n photon are being emitted, n photon means how many photons there. So let's say there are 3 packet, means there are 3 photons. Okay, per second. Then photon power P, which is an energy, total energy transfer per second, because P we learn in the P is W over T, right? So this one also P is equals to NHF. N is a number of electron. Okay, how much is number of electron? And HF is the is the energy of a photon. Means here they say the number of photon 3. Okay, there are 3 photon, 3 packets. So 3 times, okay, the energy of 1 photon. They say energy of 1 photon is 1 times 10 power of let's say -7, right? So you just multiply. So you got like 3 times 10 power of -7. Okay, and this one is actually the derivation, okay, for F, right? And this one come out from where? From V is equals to F lambda, right? F is equals to V over lambda, right? But this one V, we replace it with C because we know that the electromagnetic wave, they have the same speed as light. So we just change it to C. So you don't be confused here. C actually is the velocity, the speed of light. So then you got, we got the answer, right? So I give you one example. Okay, I'll explain to you. Identify the problem. Okay, so it have a 40 watt lamp. It means the red light wavelength. This is the lambda. All right. And what is the number of photon emitted per second? Okay, so now they ask you the number, means they ask you the value of n, number of photon. N is the number of photon. How many photon? So we want to find the n here. Okay, they give you the wavelength and they give you a power P and they give you the value of H, okay, Planck constant, and speed of light C. Okay, so we use a formula P is the power, all right, and H C over lambda. Teacher, can I just substitute in here? I don't want like to change the formula, right? Arrange it so I can find the n. Yes, just directly use the formula. I'm also suggested you do that because I'm afraid later when you try to move to find the value of n, then suddenly you produce new formula. Okay, you become another De Broglie. No, I don't want. Okay, just use this one. Just substitute inside the formula given, then find the answer. All right. So P is actually the power. So the power is N times, okay, N times HF. Okay. If you want the F, they didn't give you the F, the frequency, then you have to change it to HC over lambda. Yeah, C over lambda because the F is come from this formula. Okay. So I will stop here. So I see you tomorrow. I think maybe I try to do it on the same time. Okay, 2:30 until 3:30. Okay. So tomorrow we go to 7.2. Okay, thank you, class. Right. Take care, everyone. See you tomorrow. Welcome.
Thank you, Shah.
Thank you. Welcome.
Thanks, teacher.
Okay, welcome.